In this lesson, we're going to look at the normal distribution, also known as the Gaussian distribution, and we're going to be able to understand and describe why it's important and how it's used. And we're also going to use it to calculate the probability that a given variable that's normally distributed lies between a specified range or within an interval of values. And we'll do some other things as well, but that's where we'll start. So let's talk about the normal distribution. Here's the equation that represents the probability density function for the normal distribution. Again, this is, as I said, a probability density function. You aren't going to have to know this distribution function in great detail, but it's important that we're kind of familiar with it. And so you can see here that this function is dependent upon sigma, which is the standard deviation, both here and here, and mu as well, which is the mean. So we can also see that there's a pi and an e in here, and so this is the e that we know and love, and of course pi. And so this is a pretty complicated looking probability density function, and it's pretty interesting that it relates both pi and e as well. So just be familiar with this. Fortunately for us, we have the calculator that can do calculations for us in most cases. The things we want to do with this function would actually be pretty complicated if we were going to do them by hand. So, like I said, I'm not really going to hold you too responsible for this, but you should be aware of it and be able to recognize it. But why is the normal distribution important? Why do we study it? And there are a few different reasons. The first, and maybe not necessarily most important one, is that it describes many random processes that we see kind of in real life. A lot of variables are normally distributed or approximately normally distributed. Take the heights of people or test scores for the SAT in a given year. These distributions of these variables where you have a mean and equally likely outcomes the same distance from the mean on either side, right? So this sort of symmetric distribution of scores or of values around that mean are typically normally distributed. But there are lots and lots and lots of variables that arise in random processes, natural processes, that are not normally distributed. So by no means come under the impression that every variable is normally distributed or that most are or anything like that, though many are, and so that is an important thing to know. Secondly, we can use the normal distribution to approximate discrete distributions if certain conditions are true, and we'll look at that in class, not in this video. But the big one that we're going to look at next week is, or in future lesson here, is that the normal distribution is the basis for classical statistical inference. And that might not be clear what that phrase even means at this point, but for now, just understand that the normal distribution is really, really important as we do inferential statistics, as we do statistics that help us sort of understand different samples and things like that. We're going to talk much more deeply about that in future lessons, but this is really one of the big reasons we care about the normal distribution. So just hold that in your heads for a future lesson coming up here. Let's look at some characteristics of the normal distribution. These might be characteristics you're already familiar with. If so, that's great. The normal distribution is known as the bell curve. It's symmetric across the mean. You can see in the picture here that 50% of the values are less than the mean, 50% are greater than the mean. That's kind of why it's the mean, but more importantly, it's not only it's symmetric, right? So that curve can be reflected over the mean, and you get the same thing. Also, the median and the mode are the same value as the mean. Now, interestingly, these words, mean, median, and mode, have a different kind of meaning a little bit, because this is a continuous distribution. Up till now, we've been looking at discrete random variables, but the normal distribution is a continuous one. And so, how do you have a mode when you have an infinite number of possible values for our variable? And what does that mean? no pun intended. But what does that signify, this mode? So we'll talk about that as well. Another kind of common fact known about the normal distribution is that about 68.3% of the values lie within one standard deviation of the mean. So imagine, something like between here and here are 68% of the values within 2 standard deviations of the mean. You would have 95.4 roughly percent of the values, and then within 3 standard deviations of the mean, you've got 99.7% of the values lying in between those. So just a kind of a rough values, but a lot of times you'll hear 68% within 1, 95% within 2, and you get 99.7% probability that a normally distributed variable lies within 3 standard deviations of the mean. The 2 big characteristics of a normal distribution are its mean and its standard deviation. Now, what you see in this picture below is what happens when we vary some of those, right? So the blue curve is with a mean of 0 and a standard deviation of this is a variance of 0.2. And you can see it's kind of narrow, it's centered on 0. Likewise, the red and orange are centered on 0, the mean is 0. But they have different standard deviations, different variances. So in the red curve, the variance in the standard deviation is 1, and you can see it's flatter and a little bit more spread out than the blue curve. The variance in the orange curve, or yellow curve, is 5, and it's even more flat and even more spread out. This should make sense, right? Variance and standard deviations are measures of spread, so the higher those values, the more spread out the data. The lower those values, the more bunched together around the mean is the variable. And then lastly, we have this green curve, and what's different here is that the mean is -2, which horizontally has shifted the entire curve 2 units to the left, and it has a variance of 1/2, and so you can see what's produced there. But these 2 parameters, mu and sigma, are the only 2 parameters that distinguish 2 different normal distributions from each other, as we know from the probability density function. These are the only 2 parameters in there that could be changed to change that shape of that PDF. Now, how do we calculate a probability with a normal distribution, especially given that it's a continuous distribution? Since it's continuous and there are an infinite number of possible values for x, the probability that x is any one particular value is approaching 0. So it doesn't even matter which value that is, right? We might say, well, if I look at this picture, well, let's go with this picture. Let's take the green example here, right? Well, I might say, well, a value of -2 is way more likely than a value of -3, right? Yeah, I guess that's true, but a value of -2 exactly is just about 0, and a value of -3 is just about 0 too. So even though -2 is, I guess, technically more likely, they both have a probability of approaching 0. So how can we interpret or calculate probabilities when that's the case? And the answer is that we don't actually look at that PDF as probability values. So the values produced by the probability density function are not probabilities. You could interpret them as relative likelihoods for each of the values, but those are not actual probabilities. So what do I mean by that? Well, if we look at this, like let's again stick with the green here, the value of -2 has a PDF value, an f of x of, I don't know, what's that, like 0.575 or something, right? And a value of -3 has a value of 0.2, right? Well, it can't be the case that the probability that x is -2 is 0.575, because that would mean that the probability of 2.5 is 0.525. And if I add the probability of -2.5 and -2, I would get 0.575 plus 0.525, which I believe is 1.1. And that's not possible because we can't have probabilities more than one, especially considering that we've only counted 2 of the infinite number of possibilities for x. So these are not probabilities. These values that the PDF gives us are not probabilities and should not be interpreted that way. Now you might look at this and say, well, this is 0.575 and this is 0.2, and 0.575 for the -2 value is more than twice as high as 0.2 for the -3 value. So you could say that, I suppose, that the value -2 is more than twice as likely to occur as the value -3. But again, for any particular x value on this continuum, the probability is vanishingly small. So even that isn't very useful. So what do we do with this function? Well, the answer to that is we don't look at individual values of x at all. We look at the probability that x lies within a certain interval, not that x is a certain value. So we're looking at intervals here. And when we look at those intervals, what we look at is the area under the PDF. And you're probably already thinking about how we would calculate the area under the PDF, and you would be right that we would integrate it, right? Now you might take another step and say, oh, what was that function again? It was this, and I don't want to integrate it. And fortunately, you don't have to, because our calculator can do this for us. And so don't worry about that too much. But that is what we do, right? We integrate the normal distribution over the interval that we're talking about, and that area under that curve produces the probability. Now, what does that mean for us? Well, it means that for any given probability, any given normal distribution, right, like this red one, the area under this entire red function had better be what? Well, this is a probability density function, and so the area under that curve must add up to 1. And that's true for the red one, and that's true for the blue one, and that's true for the green one, etc. So the area under any PDF, normal or not, but in this case we're talking about normal distributions, is 1. And that's been true under the discrete variables as well, right? The probability tables had to produce probabilities that added up to 1. It's the same case here, it's just that we've got an infinite number of possibilities for x, and so we have to integrate rather than add discrete probabilities. Okay, so if I want to find the probability between two values, like let's go back to the screen, I want to know what the probability is that x lies between -2.5 and -2, forgive the non-straight lines. I would find this area, and I would find this area by integrating this curve. Now, that area, the probability that x lies between those two values, depends entirely on where that interval lies on the normal distribution, and the mean and standard deviation help determine that, right? So just as this is just a sort of an example, right? I had already said that about 68% of the values lie within one standard deviation of the mean. So you can see -1 sigma to +1 sigma about the mean produce 68% of the values. If we look at from -1 to -2 standard deviations, or from 1 to 2 standard deviations above, below or above the mean respectively, we get an additional 13.6% on either side. When you add those up, you get the 95%. And so, you can sort of see that. So, right, if we wanted, the point here is that, for instance, if I want to know the probability that x lies between 1 and 2 standard deviations above the mean, it's 13.6. And that's regardless of whatever the standard deviation or mean is, right? I don't know what the mean or standard deviation is in this picture. It's just mu and sigma. But regardless, if x lies between 1 and 2 standard deviations above mu, that probability is going to be 13.6. And we'll talk about that further as well. So what we're going to do now is take a little detour for a second and talk about the standard normal distribution. The standard normal is simply the normal distribution that has a mean of 0 and a standard deviation of 1. That's it. Okay, it's the normal distribution with a mean of 0 and a standard deviation of 1. You can think of it as sort of like the simplest normal distribution, the basic one. And when we're talking about the standard normal distribution, to sort of signify that we're talking about the standard normal, we often use z as the variable, right? So you can sort of see that on this axis. We've got the z variable here, and our nice normal distribution with a mean of 0. Now, since the standard deviation of the standard normal is 1, that z variable actually represents the number of standard deviations from the mean, right? So I mean to say that if z is 1, if this is our z value, well then that's the location that is 1 standard deviation above mean, above mu, which is 0, right? If z is 2, that's actually 2 standard deviations because the standard deviation is 1. And so it's kind of convenient. It's just like whatever z's value is, that's how many standard deviations we are either above or below the mean if z is positive or negative, right? So if this is z, then this value is negative 2.5 standard deviations from 0, right? Or 1.5 standard deviations less than 0. Okay, and that's kind of important as we move on here. So in the standard normal, z is just the number of standard deviations away from the mean, either to the left or right, depending on the sign. Why is that important? Well, when we start to go calculating probabilities with the normal distribution, we might have, we will have a variety of different normals, right? So I just did 3, right? Here's one with a mean of 30 and a sigma of 15. Here's one with a mean of 10 and a sigma of 2, and here's the standard normal, right? Let's say I wanted to calculate the probability that x here, okay, lies between 45 and 75. Now, I haven't told us how to do this yet. I mean, we know to integrate, but I haven't actually told you specifically how we'll do that yet. But I want this area, right? Well, here's the thing. 45 is 1 standard deviation above the mean, 1 sigma. And 75 is 3 standard deviations above sigma. Above mu. So that's 3 standard deviations. And so I want the area that's between 1 and 3 standard deviations above the mean. That's the same in this normal distribution as going from 12 to 16. Why is that the same thing? Because 12 is 1 standard deviation above 10, and 16 is 3 standard deviations above 10. But that's the same as going from 1 to 3 in the standard normal. Because for the z variable, 1 is 1 standard deviation above mu, and 3 is 3 standard deviations above mu. So all 3 of these shaded regions have exactly the same probability. Okay, so these are all the same area, same probability, because it doesn't matter what mu and sigma are, it matters the interval, where that interval lies with respect to mu and how many standard deviations wide it is. This is 2 standard deviations wide. It's 1 standard deviation above mu. This is 2 standard deviations wide, 1 standard deviation above mu. This is 2 standard deviations wide, 1 standard deviation above mu. And so these are all identical. And so what that means is we can actually always use the same distribution and just try to convert all these other ones into it. And that's why we care about the standard normal. So what we call that standardizing the normal distribution. So since all we care about when we're calculating probabilities is the number of standard deviations from the mean for each n, top and bottom of the interval x, for x, we can sort of convert any normal distribution into that standard normal and use the z variable. Again, the z variable is the variable for the standard normal for our probability calculations. So how does that look? Well, the z variable for any given x within, like little x within our possible x's here, is that x value minus the mean over the standard deviation. So what I mean by that is if we have some arbitrary normal distribution with a mean mu and a standard deviation sigma, and those aren't the standard normal ones, right? The mean, mu might be 30 and sigma might be 15, right? Well, the z value, let's take it as an example, this 45. I want to know what z value goes along with 45, right? What value in the standard normal is associated with the 45 in this normal, right? Well, I can see it's 1, right? It should be 1. Beginning of this interval, beginning of that interval is 1. I want to associate the 45 in the distribution I care about with 1 in the normal distribution. Well, let's look at the formula, right? Z equals x minus mu, 45, okay, minus 30, 30 is the mu, right, divided by the standard deviation. Standard deviation was 15. 45 minus 30 is 15, 15 over 15 is 1, right? And so I get a z value of 1. All we're doing here is we're taking our normal that we care about, we are shifting it horizontally by the mean, and then dividing out the standard deviation. And that's just, again, creating for us what value is associated with this x value in the standard normal distribution. And the reason that was important is that back in the day, before calculators, they had to look up these probabilities using tables. And you can't have a table for every possible normal distribution because there are an infinite number of them. Who knows what the mean is going to be or the standard deviation. What they did was they had one table for the standard normal, and then we just shifted whatever distribution we were dealing with into the standard normal and used the table to look that up, because all we care about is how wide that interval is and where it lies with respect to the mean. And so that's one reason this has become important. Now you might, you wouldn't have to use this now that we have the calculator for certain calculations, but this is actually really important for certain calculations when you are trying to calculate, for instance, the mean or the standard deviation from a given probability in an x. So you do need to know this, so please take the time to know this. It should make sense to you. Ask me questions if it doesn't. Okay, in the next video we'll look at some examples. Starting with this one, we'll do 3 examples from your homework, and hopefully that'll help you do the other ones.